So in today's class, I'll be talking about permutation symbol and useful manipulations of indical notation. So basically, for the permutation symbol, and usually in most books, you tend to see it written this way. That's maybe that or this. Anyone is fine. I'll try not to interchange them basically. So you can use any of them to represent the permutation symbol. Then if I write in lowercase, we're typically talking of vectors. So they belong to the class of vectors. So for the permutation symbol on this, so the permutation ijk, it's even if it's equal to +1, or sorry, if it's even, it's equal to +1. If it's odd, it's equal to -1. And if there is no permutation at all, we get a 0. So these are permutations of the order of 1, 2, and 3. So as I explained, you get to understand this. So basically, if you remember from the last class, from I equal to, if you permutation from 1 to 3, right, up to n, but usually we will stop at 3. So if you have a number like this, numbers 1, 2, 3, you repeat 1, 2, 3, you repeat them 1, 2, 3. Good. So with the permutation symbol, if you have 1, 2, 3, if you skip this one, you come to permutation 2, 3, 1, it's still equal. If you skip this one, you come to permutation 3, 1, 2, it's still equal, right? Good. So when you have this kind of order, it's called the even permutation. And the even permutation, you assign +1 to it. If you have this 1, 3, 2, and this 1, 3, 2, you see the order. This is 1. Instead of having 2 next, this change, there's an interchange here. This becomes odd permutation, or it's 1, or it's 3, 2, 1. Permutation does change, or if it's 2, 1, 3, then we have an odd permutation, and you have a -1. Then if we have something like a repetition like 1, 1, 1, or a permutation of 1, 1, 2, or something like 3, 2, 2, then there is no permutation at all. No permutation at all, so assign 0. So in the notation itself, it's ijk equals to, you see the order still follows ijk, 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 right? So if you skip this, the next one will be jki. You skip this will be permutation kij. So basically all these have a permutation of +1 and they are equal to each other. Now, how can an odd permutation become equal to an odd? How can even permutation be equal to an odd permutation? That will only happen if we flip the signs, right? For instance, the permutation kij can be equal to negative of permutation jik. If we look at this, right, kij. So if you want it to be equal to jik, look at this k and I switch positions. And if you switch that position, it should be followed with the negative sign. So similarly, permutation jik will be equal to the negative of permutation ikj. It will still be equal to the permutation of kji, right? Yeah, so all that happens is simply just the switching of the positions and followed by a negative sign. I hope that's clear. So let's assume we have unit vectors or like EI, E2, E3. Basically, these are like EI, right? So these three form a triad, right? Like if you have in a right-hand system, form a right-hand triad. So we could talk of the cross products. About the cross product. So I think some books call it vector product too. Yeah. So for these systems, AI times. Okay. So basically, this what I'm trying to do is like an application of the permutation symbol, right? So what I'm trying to do is like application and the permutation symbol. So if you have vectors e1, e2, and e3, typically unit vectors, right? We have a system like this way. And these vectors 1, 2, 3. Right, exactly. So they are unit vectors, meaning that this is equal to 1. Right? Good. So what happens is E1 times E1 cross E2 will be E3. If you follow the permutation symbol, right? Same way this E2. If you look at it, the order 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. The next one should be 3. We get 3. E2, 3. Next one should be 1. We get 1. E2 cross E. You say E2 cross E1. Now E2 is 2 cross E1. 1 is here, right? It's supposed to be switched, so it's become E3, but with a negative in front of it. Then E1 times E1 cross will give you 0 permutation. So if you can remember, this looks like even, odd. And this was odd, so you have to add a negative because we are flipping the sign. This was a no permutation. So basically, just a brief application of this. So just trying to show you the ideas from the permutations area. But in a subsequent video, I will give more explanation on that when you be able to build more on this knowledge. If you can also remember, if you remember like a dot product, right? So we have e1 dot ej equals to this. From the last video, we were able to get this. This represents the chronicle delta. I hope I got the spelling of this right. Chronicle delta. So this expression means e1, e2 dot 1, 2 should be 0. e1 dot e1 1, 2, 3, 2, 3, 0, 2 dot this 2, 1, that's delta 2, 1 to give you 0, right? Exactly. So that explains, this is just a side note. So you can see from the cross product points, when you have two vectors going across them, right? Looking at this diagram, you cross them, you get E3, E1, negative E, yeah. Okay, I need to be making a pointer so you can see what I'm referring to. Yeah, so E3, E1, when you cross them, right? But you see the dot, these are dot product equivalents. In the subsequent video, I'll give the physical interpretation of cross and dot products. But dot product basically is like you have two vectors, let's say B and this is A, right? Finding the angle between them, right? So for a dot product, typically it's like if you have A dot B, it's equal to this cos theta. For a cross product, you get A cross B, it's equal to A B sine theta, right? So that's the difference. And don't forget that A and B are vectors, right? This symbol means this is A and B belong to like a class of vectors or the vectors itself. I hope I've made things clear enough. So basically, we've shown the permutation symbol. And quickly, this is permutation symbol, the order with which it follows, the even permutation, the odd permutation, then in cases of no permutation. Then we've shown examples based on unit vectors, cross and dot products. Cross product, yeah, okay, let me quickly show this example. If we have this, for instance, so EI cross EJ is equal to, now look at the permutation symbol where it comes into place in those problems. EIJK EK. Does this look clear? Remember this EIJK, right? So if you're following this order, EIJ then equals to a permutation K. So this is permutation itself, and this is K, right? Good. So you can still, this can be replaced by EJKI, EIJK and EJK, sorry, permutation JKI are the same thing. They're the same thing if you remember, based on the even permutation, and it's still the same as it's KIJEK. I hope this makes sense, basically. So EI times EJ, EI times EJ, basically. So we just explained what the permutation symbol is and what it basically, and the application to cross products. Then also giving an explanation of some dot product expressions. This one previously we've talked about the chronicle delta, and if you just as a form of maybe trying to help you recall, if I is equal to j, then it's equal to 1. Otherwise, it's equal to 0. That's if I is not equal to j is equal to 0. So you can watch the last video to give an explanation on that. So now if you have a vector, let's say you have a vector A, so this vector can be expressed in form of its components. A is a vector, right? AI is the component of this vector with respect, so EI can be looked at as this base, like a vector used to describe AI. Yeah. So if you're not familiar with the terms I've just used, so I'll explain as I go further. But just know that A equals to AI EI. That is, you're just describing the components of A, or the vector A, with respect to the base. So if A is equal to AI EI and B is equal to BI EI, right? Good. This is component form. So if you do a cross product of A times B, it's equal to AI EI cross BJ EJ. Now, if you notice, you see I switch notations. I don't use I and E again. Yes, because it's a free index, right? You're not supposed to appear on the same side of the equation more than once. I is free index. You're supposed to appear in the equation more than once, right? So you're not supposed to repeat that here. That will not be tenable. So A cross B equal to, so let's simplify this expression further. AI BJ, this EI times EI cross, sorry, not times, cross EJ, right? So A cross B is equal to AI BJ. Now this expression AI cross EJ, if we look at what we've done, what we've written here, right? We can substitute that expression here. So this will be permutation, I, J, K, E, K. So this expression, this one, is now this. I hope this is clear enough, right? So the cross product of two vectors is equal to AI BJ permutation IJK EK. Yeah, I mean in your own time, as a form of practice, you can substitute. I equals to 1, 2, 3, K J and K equals to 1, 2, 3, 1, 2, 3 as well, and just see what happens basically. But this is the cross product of two vectors represented by A I B J permutation I J K E K. Right. So one useful relation you can also know is this: if you have two permutations I J M permutation KLM, it's equal to this chronicle delta ik chronicle delta gl minus chronicle delta il chronicle delta gk. So this is a relation you can write down with your notes and store. It's useful to know. Now, one way I easily memorize this is this. Now, first of all, don't forget that these terms I, J, M are, they're not arbitrary, but they are, I mean, you have the free will to choose what you want, but they're not written arbitrarily, right? So they're freely chosen by you. So you can freely choose them basically. So they're freely chosen, but but the way it is written is very important. So if you look at this very closely, okay, look at this I, J, K, M, right? So you look at I and J follow each other closely, J, K, then K and L follow each other closely, then M is separate. So if you look at this expression, I, J, K, L, M is separate, right? Good. Then if you look at this chronicle delta explanation, this I comes with, this I comes to K, this I comes to pick K, I comes to pick K, and this J comes to pick L. So you see this expression, that's how this expression is formed. Minus the other, then if you look at this expression, this I then goes to pick L, while this J and K remain together. So, I mean, well, you may not be required to memorize it, but that's the way I just simply know it. So, the first time is that, then second time is I, J, K, L. So, this I then comes to pick L, then this J and K comes to pick each other. So, it can be proven too, which I will do in subsequent class, how to prove this. Yeah, but it's a useful relation to know that the permutation IJM and permutation KLM is equal to chronicle delta IK times, IK JL minus chronicle delta IL GK and chronicle delta GK basically. So that's that. So there's some I'll call them useful manipulations that you can do with tensors or vectors and matrices itself. The first one is substitution. This is not different from anything you probably have done from a basic linear algebra class, but the only differences are about what happens to the notations itself. So typically we are used to AX problems, right? Like an AX equals to B problem is like a matrix vector multiplication. Now, if you have AI equals to, let's assume use a matrix B vector, and you have BI equals to VIM CM. Now, this will show to you clearly that, for instance, this is an expression, this is an equation, a vector AI is equals to UIM. This is a matrix. In case you can't see that, this is a vector, right? If you multiply them together, you are getting a vector. Now, we want to substitute this this Bij, this one, into this equation. Now, the b's are equal; they're the same, but we have a different notation. Here is I, and here is M, right? So if you're substituting this whole expression into this one, look at AI equals to UIM. Now, if you bring this BI, if you have to bring this BI here, if you do this IMCM, then what you'll be doing will be wrong. This is clearly wrong, basically, right? This is not equal to this. Okay, let me do that. So this is wrong because you don't just simply substitute all these values right into this. That will be wrong. So instead, what you need to do is this: from the expression bi equals to vim cm, this expression becomes bm. Now what you do is this: if you're looking at this, I here is the free index. If you remember, index is your index. Free index stands alone in this expression, and what's on the negative side should, sorry, what's on the left side should be on the right hand side. Free index I here, free index I here. M, as you guessed right, is the dummy index. So it's repeated just 2 times, right? M here. So what we're doing, so now we want to substitute, if you remember clearly, we want to substitute this one into this one into this original equation here, right? Good. But for you to do that, it has to be of the same form. So this bi, so the I will become m, I becomes m. So the free index is no longer I, but it's now m to match this. Then the dummy index m now becomes, let's say, n. Free index has changed. Then the dummy has changed too. So basically what I've just explained is the fact that we want to substitute bi equals to vim cm into a, right? Because by understanding this bm is this one is the same as this too, right? Yeah, which is this. But you cannot just substitute it without making a change of the to the index. So bm becomes, this I has turned to m, so this I here now becomes m. Then this m here, this m and this m, we've changed it to n, so it becomes n c n. Therefore, the new value after substitution will be, I mean, the right expression after substitution will be vmn cn. You understand? So basically, this is the right expression after substituting. I hope this makes sense. Now, if you look at this clearly, this expression is 3 equations, and each of the equation has 9 terms. So we have 29 terms, 27 terms in them. Well, I mean, I don't want to take time to expand this, but let me just explain by a little expand. Let me just show you what's possible with that, right? So UIM, VMN, CN, right? This I, replace it with 1, 2, 3, so it's 1M, VMN, CN plus U2M, VMN, CN plus U3M, VM, CN. Right, now this particular, if we take one of these terms, expand it, become u11v1ncn plus u12v2ncn plus u13v3ncn, right? And if you pick one of these terms again, you expand further again, you get u11v11c1 plus u11v12c2 plus u11v13c3, right? So this, of course, is these 3 terms, right? So if you look at it closely, we've gotten 3 terms from here. So if you expand this, you get 3 terms. If you expand this, you get 3 terms, which is 9 terms from just this. And if you do that similarly for this, you get 9 terms and 9 terms to give you 27 terms. I hope that's explicit enough. Okay, thank you. So the first one we've done was substitution, useful manipulation. The next one we are going to be doing this time should be in question 2. I mean, part 2 should be multiplication. Multiplication of, yeah, so if you have 2 vectors, P and Q of vectors, right? So let's assume P and Q of vectors. So if P is, let's say, A, M, B, M, and Q is a vector C, M, D, M. Now, if you want to find the product of P and Q, it's very easy to think that this should be the right answer. Unfortunately, that is not the case. If in reality, if you even look at it, this expression is not defined in the summing convention. It's not even defined, right? So it does not exist, right? Rather, what you have is, if you have PQ equals to AMBM C. Now, since you are bringing this together, you're going to change this, right? Change these dummy variables from M to become, let's say, N or DN. Sorry, DN. I mean, it's up to you to value, or you can change it to be MN, PM, C, A, D, A. I mean, it's your choice. Yeah, but usually in books, you tend to see them use I, J, K, L, M, N, maybe S, maybe T. Right? It's up to you. But as long as you follow the rules in summing convention, you should be fine with that. So so looking at that, okay. So if you have two vectors A and B, then are vectors, right? So if A, the dot product of A dot B, remembering the components AI, EI components, right? B component of B will be BJ, EJ. So we have to change these two. By component, I mean if you have if you have vector, let's draw this. Let's assume X, here's Y, here's Z. So E1, E2, E3, EI1. These are unit vectors, right? Yeah. So if A is something like this is A, the vector A. So there's a component of A in this direction, the component of A in this direction, which is A1, one in this direction, which is A2, and down in this direction, which is A3. So that's what we mean by component, right? So if you have A is equal to AI, EI, then all the components will be A1, E1 plus A2, E2 plus A3, E3. So the sum of all the components times these base vectors or the unit vectors will give you A itself, which is this. I hope that makes a lot of sense. And from previous videos, you can understand that EI, is equals to conical delta this. Right. Conical delta this way. So one useful expression you can understand is this. If you have this AI, EI dot BJ, it can still give you AI and BJ, right? Equals to AI, EJ dot product, right? And now, okay, so AI, BJ, if you remember AI dot EJ, it's conical delta JI. Right, so this. Another thing you should also remember is AI, BI is the same thing as this. BJ, that's tenable. And this is the same thing as A1, B1 if you're expanding A2, B2, A3, B3. I hope this makes sense. So the third factor, I'm trying to do any form of factorization. If you have, let's say, matrix Tij, Nj minus like a scalar, right? That just stretches Ni and it's equal to 0. So if you look at this expression, it's quite vital. Ni equals to conical delta Ij Nj. This is a very vital pattern to memorize or look out for. You see this I is a free index. It appears on either side of the expression, here or here, and it's just once. J is the dummy index and does not appear more than 2 times, which is this. Now, if you look at this closely, right, uh, this, I mean, just looking at it, you can see how this one is just 1 here, and here is just 1. So the chronicle delta uh, times this nj gives this one. It's just a useful expression to know. You can then substitute this into, you can substitute this into this, right? Now, if you look at it, this nij and this can be substituted, right? So nij minus lambda delta ij equal to 0. Yeah, I mean, if you're not, if you're okay, it's like I jumped this step, but basically what that means, like tij and j minus lambda dij and j equal to 0. So this nij, so sorry, I think I made a mistake with this one. This nij, yeah, is substituted to this, right? So when you substitute, then you bring this out of the brackets. So when you get this, then then you get this expression, then substitute to this basically. So that is the third one. Then the fourth one, we talk of contraction. We're already used to this. Contraction is when you have the index is repeated. It simply means you sum on them. So tii is simply t11 plus t22 plus t33. This is basically contraction expression. I hope this explains. I hope this video does help you understand what we are driving at. So for tensor analysis, I'm trying to show to you basically operations that are possible with tensor, right? If you're taking a course in continuum mechanics or mechanics of solids, or you need to understand this notation and how to manipulate tensors. Imagine if you have to expand an expression and you have to write out, for instance, the number of expressions is going to be too long, but with a good understanding of tensor analysis, tensor and Einstein's summation convention, you can be able to write things in a succinct manner and do that. So, as a form of introduction, basically, we've talked about the permutation symbol, which is talking about the permutation symbol, and if you follow this naive but helpful method of writing ijk, you can simply know that if anytime the order is altered, it becomes odd. But if you follow the order, it's even, which is +1. And if the order is altered, it becomes -1. If you repeat any of the numbers, it becomes no permutation or 0. Then we'll show a little application of it and what it can probably do with this. So for a cross product applications, basically, if you follow the order 1 2 3 1 2 3, if the follows the order, you get E3 even positive in front. If the order is changed, it becomes negative in front, right? Of this, because these are unit vectors. Basically, these are unit vectors, and if it's repeated, then it becomes no permutation. Then for a form of revision, if you remember from your dot product, basically, chronicle delta matrix ei dot ej will give you chronicle delta ij, and then another useful expression that you can easily remember is a cross b will be the magnitude of a times magnitude of b times sine theta. Dot product is magnitude of a, the magnitude of b cos theta. So basically we have this expression for this. EKIJ, so this one, this depends on the sign. It can be, for this one it's positive, right? Because KIJ follows the order rightly, but it can be negative if for instance we have KGI, right? So then we talked about components, and we talked about this. If you have a vector, it can be expressed in form of its components. And the component, that's to say we are describing the components with respect to a basis vector, or the direction, basically the component in that direction. The component in that direction, basically. Then a cross product, so A cross B2. We gave an expression on how that is found, and we came about this, right? And remember, the choice of I, J, M, K, or any of the numbers is yours to make. But the most important thing is the way it is written and the way it is applied. So this is another useful expression for you to know. Yeah, and I think you can prove it actually. So therefore, useful manipulations, we showed substitution and how it works, right? What is tenable and what does not, and what is deemed illegal in the substitution. Then yeah, this was just a form of revision. I did just try to show to you how to expand this. Looking at this, you have 3 equations from here, and we can get 27 terms, of which I showed to you how that was got into. Then multiplication, what is tenable and how it is done. Then I just gave like a visual representation of, you have a vector A, right? The components, the expression of the components, 2. The magnitude, these are unit vectors, so the magnitude is 1. This is chronicle delta expression. Yeah. Then factorization, this is just a basic factorization, but how you can substitute the values from this here. This is pretty straightforward from what you're used to already. Then the contraction. Basically, it's you're summing, when you double up on this, you're basically summing this up. I hope you found this video very useful. See you in the next video. Next video, I'll go through some more cross product and dot product manipulations, just to make things easy for you, and then go over the rules finally to make it easy for you to understand what we are driving towards. Thank you.